Imagine wanting to visit a star system light years away, but your fastest spaceship is barely faster than a snail compared to the vastness of space. What if there was a way to make the universe bend to your will? For centuries, humanity has gazed at the stars, dreaming of journeys to distant worlds. But there's a massive roadblock in our cosmic commute: the speed of light. It's the universe's ultimate speed limit, an unbreakable barrier that makes even our closest stellar neighbors impossibly far. That's where the warp drive comes in, a fantastical concept straight out of science fiction, promising to unlock the galaxy. But is it just a dream, or is there a flicker of scientific possibility behind this star-spanning technology? We're going to dive into the mind-bending physics, the incredible theories, and the colossal challenges that stand between us and a real-life warp drive. Let's start with the problem. You know, when you look up at the night sky, those twinkling lights aren't just pretty, they're vastly far away. Our nearest star, Proxima Centauri, is about 4.2 light-years away. That means light, the fastest thing in the universe, takes over 4 years to reach us from there. Our fastest probes? They take tens of thousands of years. Forget visiting Andromeda, our galactic neighbor, which is 2.5 million light-years away. Even if we could instantly zap ourselves to light speed, it would still take a human lifetime to reach just the closest stars, let alone explore a galaxy. The universe is unbelievably big, and our current methods of travel are, well, painfully slow. This is where the idea of the warp drive steps in, a concept that lets us sidestep the light speed limit without actually breaking it. It sounds like magic, but it's actually rooted in one of the most powerful scientific theories we have: Albert Einstein's general relativity. This theory tells us that space and time aren't just a static background. They're a flexible fabric that can be warped and curved by mass and energy. Think of it like a trampoline. If you put a bowling ball on it, the trampoline dips. That dip is what we call gravity. Now imagine we could make that trampoline bend in a very specific way. In 1994, a theoretical physicist named Miguel Alcubierre proposed a mathematical solution that, if possible, would allow a spaceship to travel faster than light effectively. His idea, known as the Alcubierre drive, suggests that instead of moving through space, a warp drive would move space itself. Here's the cool part. Picture a surfer riding a wave. The surfer isn't really moving across the water at wave speed. They're moving with the wave. A warp drive would create a warp bubble around a spaceship. Inside this bubble, the ship would be at rest, just chilling. But outside the bubble, space-time would be dramatically warped. It would be compressed in front of the bubble and expanded behind it. It's like you're standing on a magic carpet, and the carpet itself is stretching and shrinking underneath you, pulling you along at immense speeds, while you, on the carpet, aren't moving at all. From the perspective of someone inside the bubble, they're not exceeding the speed of light locally, but relative to the outside universe, they could travel many times faster than light. It's elegant, it's mind-bending, and it potentially solves the interstellar travel problem. But now, we hit the colossal snag. This brings us to the problem section. To create this warp bubble, to compress space in front and expand it behind, general relativity dictates you need something truly extraordinary: negative energy density. We call this exotic matter. It's not just regular matter with negative charge like electrons. This is matter that has negative mass or negative energy. Imagine trying to push something, and instead of resisting, it pulls you towards it. That's kind of what we're talking about. We've never observed anything like exotic matter in nature, and creating it, even in tiny amounts, is far beyond our current capabilities. Some theoretical physics hints at its existence in very specific quantum phenomena, like the Casimir effect, but manipulating it for a warp drive is a whole different ballgame. Even if exotic matter does exist, and we could somehow get our hands on it, the sheer amount needed for a practical warp drive is staggering. Alcubierre's original calculations required an amount of exotic matter equivalent to the mass of Jupiter. Subsequent work has scaled that down to something closer to a few hundred kilograms. But even that is an impossible amount for something we can't even confirm exists. And the problems don't stop there. What happens when you arrive at your destination? Calculations suggest that as the warp bubble collapses, it would release a massive burst of high-energy particles, like a cosmic shotgun blast. This Hawking radiation would essentially vaporize anything in the ship's path upon arrival, including the destination itself, and potentially the people inside the ship. Not exactly a friendly welcome committee. Then there's the steering and control issue. How do you control a bubble of space-time moving at warp speed? How do you even know where you're going when space itself is bending and twisting around you? And what about causality? If you can effectively travel faster than light, could you arrive at a destination before you even left from Earth, creating paradoxes that break our understanding of time? So, while the warp drive remains a tantalizing theoretical possibility, a beautiful mathematical solution derived from the bedrock of modern physics, it comes with a whole universe of buts. The need for exotic matter, the impossible energy requirements, the destructive effects on arrival, and the profound questions about control and causality all conspired to keep it firmly in the realm of science fiction for now. Yet, the pursuit of these impossible dreams often leads to incredible discoveries. Scientists continue to explore the theoretical possibilities of warp drives, pushing the boundaries of our understanding of physics. It reminds us that sometimes the biggest leaps in science come from asking the most audacious questions, even if the answers are not yet, or probably not. The stars are waiting, and our imagination continues to be our fastest ship. If you want to dive deeper into the universe's ultimate speed limit and why nothing with mass can unfortunately go faster than light, then click on this video right here.